Welcome to this fascinating journey into the world of animal diversity. Today, we are going to explore one of nature's most beautiful defense mechanisms, pearl formation in mollusca. Have you ever wondered how a simple oyster creates such a stunning and valuable gemstone? It turns out what we consider a luxury item actually begins as a painful annoyance for the animal. By the end of this lesson, you will understand both the biological miracle and the mathematical models behind how pearls grow. Let us dive in and uncover the secrets hidden inside the oyster's shell. To understand how a pearl forms, think about what happens when you get a tiny speck of dust or an eyelash stuck in your eye. It is incredibly irritating, and your immediate reaction is to produce tears to wash it away. In the underwater world, certain animals called oysters experience a very similar problem. However, when a foreign object, like a tiny parasite or a sharp grain of sand, gets trapped inside an oyster's soft body, it cannot simply wash it out. Instead, the oyster must protect its delicate internal organs using a much more permanent and beautiful solution. It slowly wraps the irritating object in smooth, shiny layers. Now that we understand the basic problem, let us look at the scientific specifics. In scientific terms, this pearl formation process is known as margaritosis. It is a specialized biological defense mechanism primarily observed in bivalve mollusks, such as the pearl oyster, belonging to the genus Pinctada. The entire process begins when a foreign irritant accidentally lodges itself between the mollusk's hard outer shell and its soft, fleshy inner lining. This inner lining is known as the mantle. The mantle is a crucial organ because its outer epithelial cells are naturally responsible for secreting the materials that build the animal's shell. So, what exactly happens when this sensitive mantle tissue is irritated by a foreign body? The oyster goes into defense mode. The epithelial cells of the mantle begin to multiply rapidly. They grow and spread until they form a continuous enclosed sac completely surrounding the intruder. Biologists call this structure a pearl sac. This is a brilliant evolutionary adaptation. By isolating the dangerous infection or sharp debris inside this sac, the oyster prevents fatal internal tissue damage. The irritant is now trapped, but the oyster's work is just beginning. With the irritant safely isolated inside the pearl sac, the oyster begins the next phase of its defense. The cells lining the inside of the sac continuously secrete a special composite material called nacre. Nacre is made of crystalline calcium carbonate, which provides hardness, bound together by an organic protein called conchiolin, which acts like a biological glue. As the oyster secretes this material, it builds up in concentric layers over months and years. It is this slow, steady accumulation of nacre layers that eventually forms the smooth, iridescent spherical structure we recognize as a pearl. Before we move on to the mathematics of pearl growth, let us visualize this biological process. On your screen is a cross-sectional diagram of an oyster's anatomy during pearl formation. At the top, you can see the hard outer shell. Just below it is the fleshy mantle tissue. Notice the circular structure embedded within the mantle. This is the pearl sac. Right in the center lies the dark foreign irritant that started it all. Surrounding the irritant are the concentric rings of nacre layers, slowly building outward. Below this entire defense mechanism lies the vulnerable inner body cavity, now safely protected from the intruder. Having seen how oysters naturally protect themselves, it is fascinating to see how humans have adapted this knowledge. In the real world, this natural biological process forms the entire foundation of the multi-billion-dollar global pearl industry. By understanding exactly how oysters create pearls, scientists and farmers have learned to artificially induce this process. They do this by surgically implanting a small irritant, usually a shell bead, directly into the oyster. This scientific breakthrough leads to the creation of cultured pearls. It allows us to sustainably farm pearls for jewelry and luxury goods without relying solely on the rare, random occurrence of natural pearls in the wild. While pearl formation is fundamentally a biological process, we can use mathematics to understand and predict how a pearl grows over time. Because a pearl is roughly spherical, we can model its growth by looking at how its radius increases as the oyster deposits layers of nacre. Assuming the oyster deposits nacre at a relatively constant rate, we use a simple linear equation. R of t equals R naught plus k times t. Here, R of t is the final radius of the pearl. The symbol R naught represents the initial radius of the foreign irritant. The variable k is the growth rate, meaning the thickness of nacre deposited per year. Finally, t is the total time the pearl has been growing. If the growth rate k increases due to warmer water, the final radius will increase much faster. Let us see this formula in action with a practical example. Imagine a pearl farmer inserts a perfectly round shell bead with an initial radius of 3.0 millimeters into an oyster. The oyster deposits nacre at a steady rate of 0.5 millimeters per year. We want to know how many years it will take for the pearl to reach a final radius of 5.0 millimeters. First, we substitute our known values into the linear growth equation. We set 5.0 equal to 3.0 plus 0.5 times t. Next, we subtract the initial radius of 3.0 from both sides, showing that the oyster needs to deposit a net thickness of 2.0 millimeters of new nacre. Finally, by dividing this 2.0 millimeters by the annual growth rate of 0.5, we find our answer. It will take exactly 4 years of careful farming to harvest this pearl. Now that we have calculated the time required to grow a pearl, let us measure the actual biological effort the oyster puts in. To do this, we need to calculate the total volume of nacre secreted. Since we assume the pearl is a perfect sphere, we use the standard geometric formula for the volume of a sphere. V equals 4/3 times pi times r cubed. In this equation, V represents the volume. The symbol pi is the mathematical constant, approximately equal to 3.14159, and r is the radius of the sphere. Because the volume depends entirely on the radius cubed, even a small increase in the pearl's radius requires a massive increase in the volume of nacre the oyster must produce. Let us calculate the exact volume of nacre secreted by the oyster over those 4 years. We must calculate the total volume of the final pearl and subtract the volume of the initial bead. First, we plug the final radius of 5.0 millimeters into our volume formula. Cubing 5.0 and multiplying by 4/3 pi gives a total final volume of approximately 523.6 cubic millimeters. Next, we calculate the volume of the initial 3.0 millimeter bead, which comes out to approximately 113.1 cubic millimeters. Finally, we subtract the initial bead's volume from the final pearl's volume. This reveals that the oyster secreted approximately 410.5 cubic millimeters of new biological material. This huge number highlights the immense biological energy the oyster expends just to protect itself. We have covered a lot of ground today, so let us review the most important ideas. First, we learned that pearl formation is a remarkable biological adaptation. It turns a painful intrusion into a protective masterpiece by isolating the irritant inside a pearl sac. Second, we saw that the oyster continuously secretes layers of nacre, a composite of calcium carbonate and conchiolin, to build the pearl. Finally, we discovered that this biological process can be accurately modeled using mathematics, allowing the thriving global aquaculture industry to predict growth times and measure biological effort. You now understand both the biology and the math behind one of nature's most beautiful defense mechanisms. Great job!